This video is going to be on calculating the average rate of reaction, so it's basically the last part of the reaction rates topic. However, before we go on to look at this, I'm going to begin with a starter question which will hopefully explain a little bit more, help you to understand these rate of reaction graphs a little bit better. I did mean to add this on to the end of a previous video, but technology was failing me, so we've got it here now, and hopefully it'll clear up any misunderstandings you might have had. Okay, so our first starter question is going to be all about this graph here, and the first thing I'd like you to do is pause the video and just take down a little sketch of this graph. It doesn't matter exactly how you do it, as long as it looks pretty much like the one I've drawn here. So you've got volume of gas on the y-axis, time on the x-axis. I've put units in, it doesn't really matter because I've not put any numbers in. This is just a general shape of a graph that we might expect. So, this graph was drawn after measuring the volume of gas produced over time when 2 grams of zinc lumps were reacted with excess hydrochloric acid. So you've got quite a lot of information here in the question, and if I was doing this type of question in an exam or in a test, I would want to underline some of the key information that I'm given. So numbers are always important in chemistry, so we've got 2 grams of zinc lumps. So this is telling us the number of grams, and lumps gives us an idea about particle size, so that's important when we're looking at reaction rates. And then these were reacted with excess hydrochloric acid. This word excess is also really important. This word is telling us that the hydrochloric acid is in excess. See if you can think about what that means. So hopefully you're thinking excess means the reactant that is not used up. So the hydrochloric acid is not going to be used up in this reaction. What that means is that the zinc lumps must be the reactant that does get used up. Can you think of the word that we use for the reactant that does get used up? Okay, hopefully you've remembered. So the reactant that does get used up is called the limiting reactant. And one important thing that we learned in a previous lesson was that the amount, so the mass or the concentration, we'll look at amount in more detail later in chemistry, but the amount of the limiting reactant determines the total amount of product produced. So the total volume of gas is given by the volume which corresponds to this horizontal part of the graph. So if we follow that along, whatever number would be on this axis would be the total volume of gas produced, and the total volume of gas is going to be controlled by the amount of limiting reactant, so in this case the amount of zinc lumps. Okay, so your 3 questions for this graph are, first of all, I'd like you to draw a dotted line to show what would be expected if 2 grams of zinc powder was used instead of zinc lumps. So just on your graph here, draw a dotted line to show what would be expected if 2 grams of zinc powder was used instead of zinc lumps. The thing to pay attention to in this question is thinking about surface area and how that affects rate of reaction. So the second question is, how would A, the steepness of the line, and B, the total volume of gas be affected by using more concentrated acid? So again, you've got to think, just like in question 1, you've got to think about how that will affect the rate of reaction and therefore the steepness of the line, and whether using more concentrated acid will affect the total volume of gas produced. Now, bear in mind that the acid is the excess reactant. And then question 3, draw a third line to represent the volume of gas produced if only 1 gram of zinc lumps was used. So you're going to need to copy down this graph, so pause the video now if you haven't copied down the graph, and then here are your questions again. Pause the video now and take a moment to try and complete those questions. Okay, so we'll just go ahead with the answers then. First of all, draw a dotted line to show what would be expected if 2 grams of zinc powder was used instead of zinc lumps. So the key thing here is to think about the surface area, and to remember that powder is smaller pieces than lumps. Powders will always react really fast. That's why flour can be very explosive if it's blown into the air as a fine powder. So powder has a very high surface area and it's going to react faster than the lumps. The other important thing though is that we're still using 2 grams of zinc powder, and what we're going to assume is that everything else in the reaction was the same. So the powder is going to react more quickly than the lumps. Remember from the previous lesson, the quicker the reaction, the steeper the line will be. So our dotted line is going to be steeper than the original. Another important thing to notice is that, remember we talked about how the point at which the line goes horizontal is where the reaction finishes. So the original reaction finished, I would say, about this time here. A faster reaction, so remember if we're using powder instead of lumps, the reaction is going to be faster, and a faster reaction will finish sooner. So our dotted line, what we want to make sure is that that finishes, that becomes horizontal at an earlier time than the original reaction. So just to make sure I'm doing that, what I'm going to do is I'm going to draw my dotted line coming out from here, and I'm going to keep it horizontal for a bit further back in time compared to the original reaction, to show that the faster reaction with the powder is finishing before the time at which the original reaction finished. So I've started it off steeper here. I've drawn my horizontal line going backwards here to make sure that it's obvious that it's finished quicker, and I'm just going to connect these two up in a nice smooth curve. So the gas does tend to be produced rapidly at first, and then it will gradually level off, but the curve should be smooth. It shouldn't be jaggy like that. We should have a smooth curve in terms of our gas produced. Okay, so that's the first one. Any conditions that make the reaction faster will make the line steeper, will make it finish sooner, but as long as we don't change the amount of the limiting reactant, we will still end up with the same total volume of gas. So this line here should be perfectly at the same level as the other line from the original experiment. Okay, so question 2. How would A, the steepness of the line, and B, the total volume of gas, be affected by using more concentrated acid? So A, this is just thinking about your factors that affect rate of reaction. So if the acid is more concentrated, will the reaction be faster or slower? Hopefully you're thinking faster. And if the reaction is faster, the line will be steeper. So A is steeper, and it's due to faster reaction rate. And then B, would the total volume of gas be affected by using more concentrated acid? So remember, this is our total volume of gas that would be produced, as the volume of gas that's level with this horizontal line. Now, the answer to this is the total volume of gas would not be affected by using more concentrated acid, and that is only because the acid is the reactant that's in excess. So the fact that the acid was in excess tells us that there was already more of it than we needed. It's a bit like the oxygen in the air when we're burning something. It's never going to get used up. So using a more concentrated version, using more of it, isn't going to affect the total amount of product produced. So there would be no effect on the total volume of gas produced. Now, one thing that you might consider is that if we used our acid's in excess at the moment, if we used a much less concentrated acid, probably, as long as it was still in excess, that wouldn't affect the total volume, but we might get to a point where our acid was so dilute that actually eventually there's not enough acid to react with all of those zinc lumps. So actually if you used a much more dilute acid, then they could swap places, and we could end up with the zinc being in excess and the acid being the limiting factor if we used a very, very dilute solution of acid. Okay. And then part 3, draw a third line to represent the volume of gas produced if only 1 gram of zinc lumps was used. So in the original reaction, we used 2 grams of zinc lumps, and we've worked out already that the zinc lumps were the limiting reactant. So the limiting reactant controls the total volume of gas. If we use half the amount of limiting reactant, then what will happen is that we produce half the amount of gas overall. So what we want to make sure when we're sketching this is that our line is going to finish halfway between the top line and the axis here, because we're using half of the amount of limiting reactant, so we're going to have half of the total amount of product produced. Now in this case we're not changing any other factors, so we can assume that the initial rate might be kind of similar, but because there's less reactant to get converted into product, the reaction will finish a bit quicker. So don't worry too much about the relative rate in this case, but really what you're looking for is you're looking for your line to be at half the height of the initial one. Now mine's a wee bit messy, it goes up a wee bit before it comes down. That shouldn't really happen, it should be nice and smooth, but again that would be easier if we were using actual graph paper. Right, we're going to do one more of these just to make sure you've got the hang of it. Okay, so this is starter question number 2. We've got a different graph here. This time we're looking at the loss of mass from a reaction over time. And what it says is this graph, so I'm talking about this brown line here, was produced when 1 gram of calcium carbonate lumps were reacted with excess sulfuric acid. So again, we've got a number here. We've got 1 gram, that's important, and the acid is in excess. What I want you to do is draw a line to show, sketch the graph and then draw a line to show what would be expected if the temperature were increased. And secondly, I've got a dotted line on here. The dotted line represents the reaction carried out with what mass of calcium carbonate lumps. So you've got to work out suggest roughly what mass of calcium carbonate lumps might have produced this dotted line here. So pause the video now and try and answer these questions. Right, okay, so number 1, draw a line to show what would be expected if the temperature was increased, but we're assuming all other factors are the same. So what you've got to think about is, if we increase the temperature, how will that affect the rate of reaction? Hopefully you're thinking, well, the reaction will be faster. And if the reaction is faster, how will that affect the steepness of the line? Well, it's going to be steeper. Now, this line here is about this angle. So to draw a steeper line, we've got to move it like this. We've got to move it below. If we moved it like this, that would be less steep. So a steeper line is going to be this side of this initial line. And also, just like in the previous example, a faster reaction will finish quicker. So our faster reaction is going to become horizontal quicker, so that's why I've just extended this line out here. But if all other factors are the same, then the same total mass will be lost, and the faster reaction is going to be steeper. So we go down like this. But remember, it should be a nice smooth curve. So this is my answer to question 1 here. A line which would be expected if the temperature were increased, but all other factors were kept the same. So we've got a faster decrease in mass, and the reaction levels out, it finishes earlier if we increase the rate of reaction. Okay, and then the dotted line represents the reaction carried out with what mass of calcium carbonate lumps? Well, we had 1 gram of the limiting reactant in the first experiment and we lost this much mass. Here it looks like we started up here, so that's my wee marker for where we started off. It looks like we've lost about half as much mass, so that suggests that we started with about half as much of the limiting reactant. So half of 1 is 0.5 grams. So I hope that has clarified any of the questions that you were maybe a wee bit confused with on the videos. I hope on the quiz, sorry. I hope it hasn't made things more complicated. If you haven't done the quiz yet, you should be able, if you've understood these starter questions, you should be able to answer all of the questions on the quiz quite easily now. So I maybe recommend answering the quiz questions before going on with the rest of this video on calculating the average rate of reaction. Right everyone, so we've done our starter question, now we're going to look at the main bit of the lesson, which is calculating the average rate of reaction. We're going to look at doing this based on just values, some numbers, and we're going to look at how we can do this from a graph. But first of all, a little recap about what we mean by calculating the average rate of a reaction. So we have talked about this already, but in a chemical reaction, we've got reactants being converted into products. The rate is the speed at which this happens. So the reactants are getting used up, the products are getting made, and the rate of reaction can be measured by the change in quantity of either reactants or products divided by the time taken for a particular change. That's the average rate. We've also looked at a couple of ways of measuring the volume, the quantity this quantity of products over time. Particularly what we've looked at is measuring the volume of gas produced. And we've also looked at measuring the mass lost, so that's a way of measuring how quickly the reactants are used up. So what do I mean by average rate, or why do we do this average rate calculation? Well, if we think back to our graphs that we've been looking at, what our graphs show, imagine we're measuring the volume of gas produced over time again. If you remember that the steeper the line, the faster the rate, what you'll see in all cases is that the reaction is always steeper at the beginning, so when the time is quite low, the reaction is faster, the line is steeper, and then as the reaction proceeds, this line gets shallower and shallower and then flattens out. So the rate of reaction, when we carry out a reaction with a fixed initial quantity of reactants, the rate of reaction will be fast at first and then it will slow down over time as the reactants are used up. So what we're doing when we calculate the average rate is we're taking a particular time interval and we're calculating what the rate was in that particular time interval. So that might be at the start of the reaction, it might be in the middle of a reaction, or it might be towards the end of the reaction to measure the rate at different times. So we've got an equation. This equation here is found in the first page of your data book, so you don't need to remember it, but you do need to remember how to use it and what the symbols stand for. So again, I know we went over this. If you can't remember, make sure you add this in. The delta, the little triangle, is the Greek letter delta, and that means change in. Okay, so what we're doing to calculate rate is the change in quantity divided by the change in time. And I'm going to show you how I'd like you to set your working out for this type of calculation. So, let's get started with an example. Okay, and I would recommend that you write this down so that your notes make sense. So you might want to pause the video here and write this example down. Right, so the question says, at the start of the reaction between magnesium and hydrochloric acid, the concentration of hydrochloric acid was 2 moles per litre. After 8 minutes of reaction, the concentration of acid was found to be 0.4 moles per litre, and you have to calculate the average rate of reaction. So, first thing I would like you to do when you're doing this is write down the equation. It's always a good idea to write down the equation before you substitute in the numbers. Okay, now that we've got the equation, we've got to figure out what we're looking for and what values we've got. So it says calculate the average rate, so that's what we're looking for. So what I'm going to do here is I'm going to do what I call a data column for all of the quantities or all of the values in my equation. So average rate is what we're looking for. That's what we're wanting to calculate in the question. So now I've got to look at this bit, change in quantity and change in time. And what I've got to do, because I'm trying to calculate average rate, I need to see what information I'm given in the question about the other factors in this equation. So I'm given some numbers. It's always helpful to underline numbers when you're given numbers in an equation, in a question. So I've got 2 moles per litre at the start of the reaction, and then I've got after 8 minutes of reaction, the concentration was found to be 0.4 moles per litre. So I should know that moles per litre is a measure of concentration and therefore a measure of the quantity, the number of particles that we have. So our change in quantity, it was 2 moles at the start, and then it was 0.4 moles per litre at the end. So our change in quantity is going to be 2 take away 0.4, which is going to be 1.6 moles per litre. So our concentration of acid has decreased by 1.6 moles per litre over the course of this reaction. So that's our change in quantity. And then 8 minutes, well, minutes is a measure of time. It says after 8 minutes, so we can assume that our change in time is 8 minutes. So now that I have what I've done here so far to set out my working is I've written out the equation. I've then done what I call a data column. So I've got my 3 quantities in my equation, all down the left-hand side. I've put a question mark beside the quantity that I'm looking to find out, and I've put in values based on the information in the question for the other two quantities. So change in quantity and change in time. Now all I have to do is substitute the numbers in. So average rate is change in quantity divided by change in time. The change in quantity was 1.6 moles per litre, and I'm going to write the equation, the units in here, and the change in time was 8 minutes. So you can get your calculator, or if you can do this in your head, fair enough. Okay, so I've worked out that my answer is 0.2. 1.6 divided by 8 is 0.2, but what are the units? That's a really important thing that you need to be able to figure out in any equation, and particularly when we're doing reaction rates. And that's part of the reason why I've written the units for the two quantities that we put into this equation. So what we're doing is we're doing quantity divided by time. Our quantity is measured in moles per litre and our time is measured in minutes. So really, our units are moles per litre per minute. Just as if you were doing speed equals distance over time, your speed would be in, say, kilometres per hour or metres per second. So the way to think about it is our units of rate are going to be in whatever the units of quantity are per whatever the units of time are. So I'm just going to write that out here. So our units of rate are mole per litre per min, right? But we don't tend to write per when we are writing equations and writing units in science. One possible option that you could do would be to just write mole per litre / min. And that's just to show that you're dividing moles per litre by minutes to get this final answer. So that you've probably seen that in terms of like meters per second, miles per hour, mole per litre per minute. But the way we tend to do things in chemistry is we follow a rule that you will learn about later in maths, but I'm going to try and explain it just now. So we follow this rule that if we have 1 divided by x, that is the same as x to the power of -1. So, for example, if I had a 1 over 2, that's the same as 2 to the power of -1. You can try that in your calculator if you like. Now, what that means is if I'm dividing by minute, 1 over minute, another way of writing that is if I write min to the -1. So rather than writing moles per litre / min, what we tend to do in chemistry, rather than writing in that / is we would tend to write, and that's not wrong, but what we would tend to write is mole per litre, which is just the unit of quantity, and then because it's moles per litre per minute, because we're dividing by minutes, we write min to the -1. Until you learn this in maths, this might seem a bit confusing. If this seems confusing, don't worry at all. Kind of maybe just best ignore me. If this seems confusing, the best thing to remember is that the little -1 as a superscript just means per. So this is moles per litre per minute. But this might make sense to explain why we actually do it like that in the first place. So we've looked at one example where we're just given values, and now we're going to look at how we can calculate the average rate of reaction from a graph. Okay, so actually before we look at calculating the rate of reaction from a graph, here's a little note that would be worth writing down about units of rate. So the unit for measuring reaction rate depends on how we measure the quantity of chemical. So we could measure it in mass in grams, we could measure the volume in cubic centimetres, or the concentration in moles per litre. We could use other units, but these are the most common. So we could use kilograms, but we usually use grams. So the units for rate depend on both the units of the quantity and the unit of time that we measure the rate in. So we can have different combinations. Some examples that might be worth writing down are we could have what we just had in the previous example. We could have moles per litre per minute. So like I say, it might be useful just to think of the -1 as meaning per. And that's the concentration change per minute. Another example of rate which we could have would be centimetres cubed per second, and that would be an example of the units which would be used if we were measuring the gas volume change per second. So that's centimetres cubed per second. Again, the second just means minus, the minus one just means per. Or we could, for example, measure the rate in grams per hour. So just like there's lots of units for speed, kilometres per hour, metres per second, miles per hour, there are lots of different units for rate, and the units depend on the units of quantity and the unit of time in which we are measuring the rate. And the little minus one comes from the fact that we are dividing by time. So centimetres cubed per second. This means that we're dividing centimetres cubed by second, and that's where we get the centimetres cubed second to the minus one from, because dividing by second is just the same as saying times by s to the minus one. Again, that's something you'll look at in more detail in maths. Right. So, calculating the rate of reaction from a graph. I don't really want you to copy this graph out in detail, but what it might be worth doing is making a little sketch of the graph. So I'm going to leave you to kind of wait and see how you want to do this in your notes. If you want to, you don't have to copy out the graph. What you could do is just copy out the working that I'm showing, and then you'll be doing more practice questions like this anyway. So the question says, a graph plotted from the data obtained by measuring the mass, concentration or gas volume as they vary with time during a reaction can be used to calculate the average rate. This graph shows how the mass of a reaction between marble chips and hydrochloric acid varies over time. Sorry, between marble and hydrochloric acid. So marble's just the common name for calcium carbonate. So we should be quite familiar with this type of graph. We've got a steep line initially. The initial rate of reaction is quite steep, and then it levels out. This point here, this exact point, probably here actually, where the line starts to become perfectly horizontal, is where the reaction has finished. So that would be 19 seconds, just as a wee aside there. But what we have to do here is we have to calculate the average rate during the first 7 minutes. So what we are going to do to show our working for this is, first of all, we're going to write out our equation again. So this is what we're trying to do. We're trying to calculate the average rate of reaction during the first 7 minutes using this graph here. Okay, so first of all, writing out your equation. So average rate I hope you can read my writing there. It's a wee bit messy, I know. Quite messy. So I don't have space to do this beside, so I'll just do it down here. I'm going to do my little data column. So rate, or the average rate, is what we're looking for. The change in quantity is something I'm going to need to find out from the graph. And the change in time is something that I'm told in the question in this case. So I'm told we're looking at the average rate during the first 7 minutes. So the change in time is just 7 minutes, but then it's the change in quantity that I'm looking for. So the graph shows the quantity in the mass in grams, and we start at 122.5 grams. So our change in quantity, we've got our start mass of 122.5 grams. And then at 7 minutes, so we go along the x-axis to 7 minutes, we go up to where this line is, and we go across, and then we've got to work out what the mass lost, and what's the change in mass, because remember this is all about the change in quantity, so what's the change in mass from the start to where it is at in 7 minutes. So we just need to try and work out this scale here. Each of these big spaces is 0.1. So each of these little spaces, there's 10 little spaces between between where the quantities are marked. Each little one must be 0.01. So this is 122.32 at the end, at 7 minutes. Okay, so 122.3, another way you could say that's halfway between 122.3 and 122.4 would be 122.35. and then so therefore each of these little ones means an increment of 0.01. Okay, so to work out the change in quantity, I've got to take the mass at 7 minutes away from the mass at the beginning. So it's just always the bigger number take away the smaller number. So 122.5 take away 122.32 gives me 0.18 grams. So my change in quantity is that we have started at 122.5 grams. We've started at 122.5 grams. After 7 minutes, we only have 122.32 grams. So I'm taking away 122.32 from 122.5 to tell me that we have lost 0.18 grams in the first 7 minutes. So that's our change in quantity in the first 7 minutes. Now that we have worked out the change in quantity and the change in time, we just need to substitute these values back into the equation. So we've got 0.18 grams divided by 7 minutes. So again, get your calculators out. Okay, so when I do this sum in my calculator, I get quite a number with a lot of decimal places. Generally in chemistry, I would recommend rounding to 2 significant figures or 2 decimal places, whichever probably gives you more figures. So I'm going to round this to 2 significant figures. So 0.0257, we've got 57, so that would round up to 6. So my answer is going to be 0.026. And my units are going to be grams. Remember, we did grams divided by minutes, so it's going to be grams per minute. And we show the per with a little -1. So we've got 0.026 grams per minute for that one. Okay, just to check whether you've got the hang of it, I'm going to ask you to do this one last question. You don't need to copy out the graph or any of the question, but I just want you to check, try and have a go at doing this yourselves. So what you've got to do is you've got this graph here, which is volume in centimetres cubed versus time, and it's asking you to calculate the average rate during the reaction between 10 and 15 minutes. So remember, you're going to write out your equation, average rate, change in quantity divided by change in time. You can abbreviate it if you want to, I don't mind. And then you're going to use the information in the graph to work out what the change in quantity is and what the change in time is that you need to put into this equation. So average rate is what we're looking for. Change in quantity, you're going to have to work out from the graph, and change in time, you also have to work out from the graph or from the question. So we're going from 10 to 15 minutes, so you need to work out what time interval that is. Okay, give that a go yourself, and then I'm going to quickly run through the answer. So make sure you've paused the video. Okay, so to just go over this question then, we were looking for the change in quantity and the change in time to then use the average rate equation. So you can see from the graph at 10 minutes we had 100 centimetres cubed, at 15 minutes we had 130 centimetres cubed of a gas. So our change in quantity is going to be 30 centimetres cubed, so you should have written that in here. Our change in time was from 10 to 15 minutes, so hopefully that's nice and clear. That's just a change in time of 5 minutes. So when we come to do the sum, what you're doing is average rate is change in quantity divided by time, divided by change in time, so that's 30 divided by 5, so 30, and again I put my units in, divided by 5 minutes, and 30 divided by 5 gives us 6, and then the units are centimetres cubed. We're dividing by minutes, so it's per minute, min to the -1. So you can see that written out a little bit more neatly here. Okay, hopefully you've got the hang of this. I'm going to post another video which explains it in a slightly different way in case you didn't find my explanation quite clear enough. Make sure you check the other video out if you're not sure from watching my video, and I'm going to post you a load of examples to do on this. It's really important that you get the hang of this calculation. It's not too difficult a calculation, I don't think, and it's one that can pick you up a few marks in the exam.